So one of the claims that we made while doing examples was that if you have a set that has a minimum, so a set that has a lower bound in the set, then that member has to also be a greatest lower bound, or it's also got to be the infimum. So let's show that that's actually true. So our claim is if A is a member of the set capital A and A is the minimum, then A is also the infimum of the set. Okay, so let's prove this. Well, since A is a minimum, well, that means A is a lower bound for capital A. That's just another statement of the definition of minimum. Now, what we want to show is that this is therefore the greatest lower bound that we could possibly have. All right, so let's suppose that A is not the infimum, so that there's some other lower bound that's actually greater than A. So let's suppose A is not the infimum. Then there must be some other lower bound B such that B is a lower bound and B is greater than A. Right? That's what it would mean for A not to be the infimum. There's going to be some other lower bound that's larger. But right here we already have a contradiction. In order for B to be an infimum, B has to be a lower bound for the set. So every member of the set has to be larger than B. A, we assumed, was a minimum, so it's in the set, but it's not larger than or equal to B. So if we try to arrange for a larger lower bound than A, we violate the fact that it's a lower bound at all. All right, so that brief proof shows that if you have a minimum in your set, it's automatically the infimum, and the same kind of argument holds for a maximum and supremum. And I think you get to try that one.